Hello, everyone. Today, we'll explore the zero-penalty self-contained binary performance monitoring solution, developed as part of the D6G project. The presentation will be structured into 5 chapters: problem statement and motivation, implementation, results, conclusions, and future work. We'll start by the problem statement and motivation. Our goal is to develop a zero-overhead self-monitoring performance solution. It should be able to detect performance variation caused by external factors like a remote attack or internal ones, such as a local machine malfunction, all without adding any penalty to the monitored process. Now let's take a look at the limitations of existing monitoring solutions. First, some of them can't recover runtime information from infinite lifetime softwares, which limits their applicability in long-running or critical systems. These tools typically require a defined start and end point to generate meaningful performance metrics. As a result, when a program runs in an infinite loop without a clear termination, it becomes difficult to measure its performance accurately. Our approach addresses this by inserting checkpoints within the program's loop, allowing us to measure the time between checkpoints and analyze their frequency. Second, many existing tools come with numerous dependencies, which increases integration complexity. Additionally, they often introduce a significant performance overhead, distorting the very behavior they are intended to observe. Finally, many monitoring solutions are designed to operate with elevated privileges, making them unsuitable or even unusable in restricted, embedded, or production environments where such permissions cannot be granted. Let's look at a few examples by evaluating existing solutions against these criteria, ranging from negligible to most critical. Intel vTune introduces moderate overhead, requires Intel drivers and GUI tools to operate, and demands elevated permissions. Perf performs reasonably well, but it often requires root access and relies on specific program events and symbol information. Valgrind operates with user-level permissions, but it drastically slows down execution by a factor of 30 to 50 times, which is clearly unacceptable. Our motivation is to develop a zero-overhead solution that runs entirely in user space, requires no external dependencies, and offers high granularity. To evaluate our solution, we rely on 3 key performance indicators. First, accuracy, which reflects how precisely we detect performance variations. Then, penalty, which measures the overhead our monitoring introduces, ideally as close to 0 as possible. And finally, convergence, which tells us how quickly the system can perform a measurement. Improving one KPI often reduces the performance of the others as they compete for resources. Balancing these KPIs is essential for optimal monitoring without disrupting the observed program. Let's now dive into the implementation. Our solution is designed to work with both finite lifetime and infinite lifetime software. Monitoring the performance of finite lifetime programs is relatively straightforward as their total execution time can be measured directly. In contrast, infinite lifetime software must be monitored at the code block level, since blocks have a finite lifetime and can be measured independently. To understand how our solution operates, let's delve into the analysis process. We start with the original binary file, which undergoes both static and dynamic analysis. This dual approach allows us to thoroughly examine the file under normal operating conditions. From this analysis, we extract crucial blocks data and control flow information, which are essential for understanding the behavior and performance of the system. This comprehensive analysis forms the foundation of our evaluation, enabling us to make informed decisions based on the needs. Now that the analysis phase is complete, we move on to the second step, statically rewriting the binary. Based on the collected analysis data, our algorithm identifies the most relevant blocks to instrument. The identified blocks are then patched, resulting in a patched binary file that includes monitoring functions. Finding the most suitable blocks is the key for the algorithm. These blocks should accurately reflect the overall performance of the binary with high reliability, without compromising performance. And we'll come back to this crucial selection process a bit later. After patching the binary, we move to the third step, detecting performance variation. The patched binary now includes embedded monitoring functions. As the binary runs, these functions collect performance data in real time. This live data is continuously compared to the reference performance gathered during the initial analysis phase. If a significant deviation is detected, in other words, if the current performance diverges from the reference, an alert is triggered. The detection behavior is highly configurable, allowing fine control over parameters such as the time window for detection, the variation threshold, and the ability to filter out outliers, ensuring robustness and adaptability across different use cases. Now that we've explained how performance variation is detected, let's take a closer look at what we're actually measuring. In our system, we focus on 2 key metrics: execution time, how long a basic block takes to execute; call frequency, how often that block is executed during a run; These two metrics are extracted at the control flow code block level and are chosen not only because they provide critical insights into program behavior, but also because of their universality. By relying on such fundamental and architecture-agnostic signals, we ensure our monitoring and detection system remains lightweight, effective, and broadly applicable, regardless of the underlying application. Now, let's take a closer look at what can actually cause these values to change during a program execution. We can broadly categorize these influences into two groups. Exogenous factors are external to the program and depend on the execution environment. These include CPU sharing with other processes, variations in instructions per cycle, and CPU interruptions. Endogenous factors are internal to the program or come from its interaction with the operating system. These include I/O and data operations, cache usage, and system calls. All of these factors can cause visible changes in our performance metrics. Pinpointing every individual cause would be very difficult, so instead we use both execution time and call frequency to distinguish between these two broad categories. Execution time is one of the most direct indicators of how a program is behaving. After we carefully selected a set of specific blocks that we believe are representative of the program's behavior, like block 2 in this example, we measure execution time by recording timestamps by inserting two trampolines into each selected block. One trampoline is placed at the entry point, and the other at the exit point. These trampolines are tiny pieces of injected code that record the current timestamp. The difference between these two moments gives us the time it took to run that specific block. Call frequency gives us insight into how often specific blocks are executed. Here, as the program runs, each time block 2 is entered, a trampoline records a timestamp. To compute the call frequency, we simply take the number of recorded executions and divide it by the total elapsed time. This metric requires a good understanding of the program to be effective, as call frequency is both control flow and data dependent. By instrumenting the right locations in the code, we can accurately capture the program's capacity to process a given amount of input data per unit of time. During the testing phase, we encountered a significant issue that repeatedly disrupted our measurements. Let's illustrate it using this example of instrumented blocks. As shown earlier, we patch each code block with a trampoline at the entry and another at the exit. Here, we simulate two consecutive blocks, each patched in this same way. To measure execution time, we record the timestamp at the block's entry and subtract it from the timestamp at the exit. Now, let's walk through the normal execution. We start at entry 1, where the first timestamp is recorded. The instructions of block 1 are then executed. Upon reaching exit 1, the second timestamp is taken. Subtracting the two gives us the correct execution time. The same process works fine for block 2. We record at entry 2, execute the block, and record again at exit 2. However, a problem arises when exit 2 is a conditional jump, where the target address is computed dynamically and may vary at runtime. In this scenario, the jump takes us back to block 1, but bypasses entry 1. As a result, no new timestamp is recorded at the beginning of block 1. When we eventually reach exit 1, a timestamp is captured, but it's not paired with the corresponding entry time. This leads to invalid or misleading measurements. This highlights a fundamental undecidability issue. Since the jump target is not known statically, it becomes impossible to guarantee accurate entry/exit pairing in all execution paths, especially in the presence of loops or data-dependent control flow. One way to address this issue would be to simply discard the invalid measurement and wait for the next valid entry-exit pair. While this might work, it's not reliable and can lead to inconsistent data. Instead, we opted for a more robust and long-term solution: the reference block. It is our own custom block, designed to replace reliance on original application blocks. Its purpose is to guarantee that both the entry and exit points are always reached and that the same set of instructions is executed every time, regardless of the application's behavior. It works by combining both call frequency and execution time into a single mechanism. Each reference block includes two timestamp instructions along with a fixed set of operations, all placed within the same block. The reference block is then inserted alongside the program's original blocks. This consistency significantly improves measurement accuracy by reducing variability and ensuring reliable results across multiple runs. However, one major challenge remains. Instrumenting every block typically results in an unacceptable performance overhead. Instead of instrumenting everything, we could carefully select just a few key blocks, those that provide the most insight into system behavior. But with hundreds or even thousands of blocks, how do we decide? That's the challenge we're facing here. To make the right choice, we rely on three key factors: call frequency, variability, and regularity. Let's illustrate these three key ideas. Call frequency refers to how often a block is executed. For accurate measurement, the block must run frequently enough for the trampolines to collect sufficient data. Variability relates to the stability of that frequency. We want blocks with consistent behavior. not ones that run once, then suddenly 10 times in the same time window, or only at the very start or end of execution. Such blocks don't offer useful insights about ongoing performance. Regularity means the block should be consistently executed across multiple runs. This allows us to compare results reliably and detect meaningful performance changes. So, the ideal block is the one that strikes the right balance. It should have great regularity, meaning it's consistently present across runs. It should also show mid to high call frequency so we collect enough data without increasing the penalty too much. And finally, it should have low variability, ensuring stable and reliable behavior over time. Now let's go behind the scenes and see how the monitoring actually works. Earlier we mentioned that we're patching the binary using E9 patch. But let's dive deeper into what's really happening under the hood. When a selected block is executed, the trampolines we inserted earlier get triggered. These trampolines are responsible for collecting data in real time. We use a shared memory segment to store the data, making sure the communication is fast and efficient. On the other end, a lightweight reader process continuously monitors this shared memory. This process handles the reading, post-processing, and saving of the data, or could even serve as an alert trigger when something unusual is detected. The data is then either saved to a CSV file or sent to a remote machine. Before we go any further, let's take a moment to talk about our test environment. Most of our evaluations focus on CPU stress scenarios. For finite lifetime software with a fixed set of instructions, we used Prime's calculator, a custom CPU-intensive application that calculates the first 1 million prime numbers. To generate controlled and repeatable stress conditions, we applied stressing directly on the machine running the monitored program. This setup allowed us to precisely manipulate CPU load and observe how our monitoring system responds in real time to evaluate our KPIs. For infinite lifetime programs, we used L2 forward. Traffic was generated using T-Rex from a first virtual machine, reaching up to 1 gigabits per second. Measurements, such as execution time or call frequency, were collected from a second virtual machine where L2 forward was running, while stress was applied locally via stress-ng. Traffic statistics were gathered directly from L2 forward's internal counters. With the test setup clear, we can now dive into the results we've gathered so far. First, let's look at some results from our finite lifetime program tests. In this case, we applied CPU stress to the machine running our Prime calculator with every block entry instrumented. The goal was to determine whether the program's performance could be correlated to the stress applied to the system. This graph shows the total time required to calculate the first 1 million prime numbers, plotted against the number of CPU stress workers on the machine. The almost perfect correlation between stress and performance demonstrates that for a fixed set of instructions, the program's execution speed is heavily influenced by the amount of stress it experiences. Now the question is, can call frequency give us a real-time indication of the program's current performance? Let's find out. This graphic shows the call frequency of our reference block versus stress level, measured as the number of CPU workers used by stress-ng, along with 3 estimations obtained using linear interpolation. As you can see, this method can estimate the stress level experienced by the program, with an error ranging from just 13% down to as low as 1%. Its main advantages are that it's extremely easy to implement, requires very little computation, and works well for local estimation. However, it has notable drawbacks. It performs poorly for extrapolation beyond the measured range, it is sensitive to noise, and it assumes a roughly linear relationship that may not hold under all conditions. Now, moving on to the modeling method. This approach derives a functional equation of program stress degradation from collected performance data, allowing us to map observed metrics, such as call frequency, to estimated stress levels. In our tests with the Prime calculator, we obtained a fitting function capable of estimating applied stress with errors ranging from about 10% down to as little as 0.1%. Its key advantages include improved prediction accuracy, greater resistance to noise, and the ability to provide more meaningful insights into performance trends. However, it also has drawbacks: reduced precision at very low stress levels, and a higher computational cost compared to linear interpolation. In one of our first tests as an example of an infinite lifetime program, we used L2 forward from PCAP++, a high-performance C++ packet capture and processing library. We patched all entries of all blocks and all functions, then compared its behavior under normal conditions and under CPU stress. The results show that when CPU stress is applied, function call frequency drops by a factor of 7, while block call frequency drops by a factor of 15, indicating a substantial slowdown in how often code segments are reached. For average execution time, the effect is inverted. Functions run 7 times slower on average, while some blocks run up to 15 times slower. This difference occurs because function execution time is averaged over all its blocks, including those executed only once, so faster or less affected blocks dilute the slowdown, whereas block execution time isolates individual instruction sequences, revealing extreme slowdowns that get hidden in function-level averages. Although patching every block introduces an unacceptable performance penalty for production use, this experiment clearly demonstrates that both metrics, call frequency, and execution time can be used together to detect CPU stress and performance degradation in real time. An important phenomenon we observed is process switching, which occurs when the operating system's scheduler switches between processes. These context switches temporarily pause the monitored program and can have a significant impact on our performance metrics. Both of these graphs show L2 forward static patched on several blocks. Notice how, under CPU stress, execution is interrupted regularly compared to the normal run. These interruption bands, typically lasting 10 to 20 milliseconds, break the program's flow into execution bursts. But how does this affect our metrics? First, if a context switch occurs during the execution of the reference block, it artificially inflates its execution time, making it appear slower than it really is. This introduces noise and variability into our execution time measurements. Second, if the interruption happens right after a block finishes, it delays the next block call. This reduces call frequency since fewer executions fit within the same time window. In both cases, we observe the same effect, a decrease in call frequency and an increase in execution time. Interestingly, this recurring pattern itself becomes a strong indicator of CPU-related disturbances. From these illustrations, we can already see that call frequency is highly sensitive to interruptions, while execution time only shows them if a context switch occurs between its two timestamps. This means that when using execution time, the reference block needs to be long enough to capture performance variations. For example, in this L2 forward test, we compare a reference block with 0 instructions to one with 2 million nope instructions, under CPU stress ranging from 1 to 10 workers. The effect is clear. The block with more instructions shows a much stronger correlation to the program's performance. Another interesting finding concerns the versatility of call frequency. We observed that call frequency is highly dependent on the program's control flow, which makes it possible to monitor almost any specific part of a process loop. This means it can provide a real-time view of the performance of that particular section of the program. For instance, in this example, we placed our reference block inside the code responsible for packet forwarding in L2 forward, and as a result, the call frequency is strongly correlated with the number of packets sent. Let's move on to the conclusion, beginning with the most important aspect of call frequency. It is highly dependent on control flow and input data. If the control flow does not trigger the reference block, no information about the program's performance can be obtained. However, this aspect also makes call frequency very flexible, allowing us to extract metrics for any specific treatment or loop per unit of time. For example, traffic volume in the case of L2 forward. Next, let's move on to identifying the causes of performance degradation. Call frequency is sensitive to both exogenous and endogenous factors, while execution time is only influenced by exogenous ones. By comparing both metrics together, we gain a way to determine whether performance variations originate from internal behavior or from external system factors. We can clarify this by illustrating a sequence of instructions into which our reference block is inserted. Exogenous causes can affect all instructions, including those within our block, whereas endogenous causes can only influence instructions outside the block. Since execution time measures only our block's instructions, it inevitably ignores the original program's instructions. This limitation comes from the nature of the block's instructions, which are usually designed to be sensitive only to exogenous factors. For example, nope instructions can still be influenced by exogenous factors such as IPC variation or CPU interruptions. However, they do not perform system calls, do not access caches, and do not depend on variables or data inputs. Let's move on to the usability of both metrics. We'll organize the conclusion into 3 parts: finite lifetime programs, infinite lifetime programs, and overall global insight. First, regarding call frequency, we have seen that its instrumentation within blocks depends on both control flow and data. For execution time, regardless of the lifetime type, the instructions in the reference block must be long enough to capture resource congestion. Concerning call frequency in a finite lifetime, using the same operand consistently delivers a very accurate measure of stress level and performance. Additionally, the monitored block should be selected with care, taking into account its intrinsic call frequency and regularity. Execution time can be measured over the entire program execution, thereby providing a highly accurate measure of stress level and performance. Finally, for an infinite lifetime, call frequency, when placed at the appropriate location within the process control flow, can directly capture operational values such as L2 forward's ingress volume or egress throughput. This makes it possible to detect anomalies such as denial of service attacks. Within the same lifetime type, a nope-based reference block is semantically neutral. It does not solicitate the cache, I/O, data, or system calls, and therefore can help identify the specific cause of performance degradation by eliminating these performance variations associated causes from the set of possible causes. What about our KPIs? First, in terms of accuracy, we can reach up to 99%, but this depends heavily on selecting the right reference block and also on the type of program we are analyzing, whether it's finite lifetime or infinite lifetime. Next, convergence depends on how often the reference block executes. The more frequent, the faster the metrics converge. For example, on the primes calculator, we achieved 95% accuracy within just 200 milliseconds. However, convergence can also be influenced by noise or aberrant values, which may slow it down or introduce variability. Finally, when it comes to penalty, through architectural choices and reference block optimization, we've managed to reduce the overhead to just 0.1%, making the method both lightweight and practical for real-world scenarios. Let's wrap up this demonstration by looking at some possible directions for future work. Earlier, we noted that because of the nature of NOPE instructions, execution time cannot capture variations caused by endogenous factors. A possible future extension would be to design multiple reference blocks tailored to measure and detect stress linked to specific endogenous factors, such as cache behavior, system calls, or data dependencies. Similarly, with call frequency, instead of relying on a single measurement, we could patch multiple blocks and monitor them in parallel to identify choke points or pinpoint specific performance variations. Together, these improvements would provide a more complete picture of performance changes and enable finer-grained diagnosis of their root causes. Thanks for watching.